Okay, hello everyone. So in this video, I wanted to go over a lemma for a problem in my rings and fields class. And basically what this lemma was saying is that the binomial theorem right here, where I've written it down, is true in a commutative ring R for any element A, B in the ring R, right? Um, and just as a note, this n here is an integer, and so is this coefficient. So that's why this multiplication here is different than, the implicit multiplication here, which is the rings multiplication. And, to prove this is basically just induction, or it is induction. So we show it's true for some n equals to 1, sorry. So we just consider what this is. This is just a plus b. And likewise on this side, we would get something like, you know, 1, 0, a to the 1, b 0, plus 1, 1, a to the 0, uh, b to the 1. And this is just a plus b, right? I mean, if I wanted to be more precise, I would just write this as a plus b, and then this in a separate line, and that's a plus b, but it's whatever. And then given this, which is our base case, we can just assume this is true for n greater than or equal to 1. And then we're going to consider the n plus 1 case, which is like this. We can split this to something like this. And then by the inductive base case, we get something like this, where this is the sum that we had earlier. And then since we're in a ring, we can do left distribution or right distribution, but in this case, it's left distribution. So we're going to move this A to like right here and this B to right here for two different sums, right? And since we're in a commutative ring, which is important here, we can move these ring, what do you call it? We can move these ring elements, right, over, because right here, the A would end up somewhere here, and the B would end up here too. But for the B, you wouldn't be able to merge it into this power if it weren't commutative. So that's why it's important for it to be commutative. The reason I'm explaining this instead of writing it down is because I don't want to write down all of that. So from there, we get something like this. A to the n minus k plus 1 to the bk plus the same thing, but with the b. Right? And then from here, I'm pretty sure it's just like index real. Okay, so sorry for the cut. I realized I made a mistake in my work, so I had to cut it out. But basically, from this step, what we're going to do is rearrange the sums, more specifically this right-hand sum, with the intent of using Pascal's identity. So this left sum stays the same, but we move over this sum on the right by 1. And we're going to get something like, we want this to be n choose 0 to n choose n. This is going to start at 1, so we subtract by 1. We're going to start at 0 here. We're going to start at, then we're going to start at 1. Wait, no, we're going to start at n here, and then we're going to start at n minus 1. So we add 1, right? Here we're going to start at 1. And that's going to happen naturally here, so we subtract 1, right? And then we take out terms from both sides. Um, specifically for this one, we take out k equals 0, so we get this, right? Let me know in the comments if you think my a looks like the number 2. I don't, but other people have told me that. And then on this side, we take out the n plus 1 term to match with this n plus 1 over here. Hey, and then while I'm erasing this, what we're going to do after this is use the aforementioned Pascal's identity. I'm just going to write it down here, and I'm not really going to explain it because I kind of just memorized it myself, but I'm pretty sure it comes from Pascal's triangle, and like an item either above or below on that triangle being equal to the, no, it's the item below is equal to the one, is equal to the 2 items above it, I'm pretty sure. Right? So like you have like an item here and it's equal to these 2 ones, or the sum of those 2 ones, right? But besides the point, we're just going to use it, okay? So then we get this, right? These 2 choose coefficients, they're going to combine. And then we're going to get this. A to the n. I'm going to write it like this now. Okay, so we get this. And something you can notice is that when this k, if this k were to be equal to 0, right? Then we're going to get this term, right? So I'm going to move this k to 0, right? And if this max were to max out at n plus 1, then we get this term, right? So I'm going to move this up to this. And this is basically what we were trying to prove. So and we are done. I hate that this is called a lemma because it's so long, but yeah, we're done. So if you have any questions or if I did anything wrong, leave a comment below. But yeah, that's pretty much it. So goodbye.